Good morning. This is the AP Calc video for section 6.2. It's the last video for section 6.2. And as you can see, this is finding volumes of solids with known cross sections. And what's important here is everything we've done so far in this section has been about revolving a region around a line to create a three-dimensional figure. And so far, the cross sections have all either been disks or washers. And then we use the appropriate formula depending on which one of those it was. Well, the last type of solid that we'll find the volume of is if we still have a region, but this time instead of taking the region and revolving it or rotating it around an axis, we are just the region will be the base of a solid, and we're just going to kind of build a solid up with a particular cross section, which the problem will tell us. So this should be as straightforward as one example in the notes here, and then you'll do, I think it's just 4 examples for an assignment, and that'll be the end of our volumes topic. So here we go. We've seen this region before. Let R be the region bound by the curves y equals x squared and y equals root x. The region R is the base of a solid whose cross sections are squares perpendicular to the x-axis. Find the volume of the solid. So I sketched the region. The top, there's y equals root x, and then the parabola y equals x squared. So, but we're not rotating this around anything. We are just creating a solid. So I'm going to, just like before, I'm going to just draw one typical cross-sectional rectangle. Let's go just right about here. It doesn't really matter where I go. I'm drawing one rectangle. Instead of rotating that, picture whatever length that side length is. Picture a square coming out from the page that same distance, like a square cross section with thickness dx still, like this. So there would be a square down here. This cross section might be a little smaller. This cross section might be a little bigger. Again, difficult shape to name, but pretend that this region is flat on the table, and if that green rectangle happens to have a length of 3/4 of an inch, picture a square coming out 3/4 of an inch from the page. So each cross section is a square with thickness dx. So in this case, we just have to be aware of what the cross section is, and it's a square here. The perpendicular to the x-axis, that just means my thickness is going to be a dx thing, not a dy thing. That just means that's going to be a dx issue. So to find the volume, well, how do you find the volume? If I had a square with thickness, like a square prism, the volume of one of those would be length times width times height. Now, of course, the height is dx. The length and the width are the same in this case because it's a square. So it would just be I'll use the letter S carefully for side length. It'd be the side length squared times, I guess I can use the height. Like I'm thinking, let me go over here. If I had picture a square, that last line was awful. Picture a square, that's side length, and that's side length, and that's the height. To find the volume, that would be length times width times height, or S times H. And so that's the side length squared times the height. So turn that thing vertically, and that's what one of these green rectangles would look like if I had it come out from the page. So the volume is S squared H. So the H, we already decided that's going to be my dx. That's the thickness. As far as the S, the side length. Well, the side length goes from here to there. Like that. That distance is what I'm calling S. So how do I find that distance? Well, again, you have to remember that that's the difference between the two curves. So from 0 to the top, so let me change colors here. So let me put this over here, dotted line over there. So from 0 to that y value, that's the y, that would be the y value of the upper function, which is root x. And if I change the blue, The smaller distance, which is from 0 to there, that distance right there is the y value of the lower curve. That's x squared. So I put all that together, and my side length becomes the difference in those two y values, which is root x minus x squared. So you're rarely going to see really complicated ones for this one. It's of all the things you're likely to see, the ones where you're revolving something around an axis show up more often than these. But this is actually not any more difficult. Remember, since we're not revolving anything, there's no circular anything. So don't default to putting a pi outside the integral, which is tempting because everything else we've done so far has started with pi r squared h for a disk, or pi big R squared h minus pi little r squared h for a washer. There's no pi here because the cross section's a square. So now let's write this as integral. So the volume would be the integral now from what to what. These rectangles inside the region, which become square prisms, go from x equals 0 to x equals 1. Remember, if the curves were weirder, you may have to set them equal to figure out where they intersect. I think you know what these curves look like, and I gave you the 0.11. So we know the x's go from 0 to 1 here. Integral from 0 to 1 of the side length squared, so that's root x minus x squared, the side length squared, and then the thickness of each cross section is dx. And just like the last ones, now it's just a matter of taking the integral. So let me go like this, let me do that. Okay. So now I need to do some algebra first. I am going to multiply root x minus x squared by itself. Again, I'm writing it like I'm just going to, well, I was going to try to just think it, but I'm rewriting it like this, and I'm just distributing. And if you can write that part in your head and then just start using distributive property, that's fine. So if I distribute that, I get that this first part of the distribution is just x, and the next one is I add exponents. That's minus x to the 5 halves, and this is again minus x to the 5 halves. That's minus 2x to the 5 halves, and then my last part of the distributive property is plus x to the 4th. So there's my integral. Now I can take the antiderivative. This is x squared over 2 minus, let's see, 2 times x to the 7 halves over 7 halves. And over 7 halves means times 2 sevenths. I believe it becomes x minus 4 sevenths, x to the 7 halves. That's a 2. And then plus x to the 5th over 5. That evaluated from 0 to 1. Again, in this example, I like the fact that it's at 0 because when I evaluate that at 0, it's going to be nothing. So this is, I evaluated at 1, I get 1/2 minus 4 sevenths plus 1/5. That's one fraction line. And then officially minus 0 plus 0. If I make all that 70th, I think is my common denominator, I get 35 70ths minus, let's see, times 10 minus 40 70ths, and then plus, let's see, times, what's that, 14 70ths. Turn out to get negative 5, turn out to get 9 70ths. Units cubed would be the unit. It's a three-dimensional figure. So there's just a real hopefully straightforward example. Again, pay attention to what shape the cross section is, whether it's perpendicular to the x or y axis, because if it was perpendicular to the y axis, it would be a dy thickness thing, which we saw. And then just make sure you use the right formula for whatever shape the cross section is. So that's it from the example. Your homework is these 4 problems. Just while I've got you here, I think one is a square, one is a rectangle where height is 1, so it's just the side length times 1 dx. And then one of them's a square, one of them's a semicircle, where it's just 1/2 of pi r. That one would have a pi because the cross section is semicircles. I believe that's that last one. So that's all I've got. Have a great Monday.